In this video, we are going to run a significance or a hypothesis test for means, where we are looking at matched pairs. So what we're going to be doing again is finding the difference between two quantitative numbers, and then we're going to be running really just a one sample t-test for means on just the difference. So really our conditions are identical to a one sample t-test. We're just going to call this a paired t-test. Okay, so our conditions are random. Just going to go through these very quickly, not reading everything on my screen because we've done this several times and it's in previous videos. Feel free to stop, pause the video and read more carefully. So random, 10%, and our large counts or normality condition, where we're dealing with whether or not we have a small or large sample size. Okay, so we are going to be calculating our t-test statistic. Again, we're going with a t-test because we rarely will ever know our population standard deviation. So we estimate with our sample error. So what we're going to be doing is we're going to be assuming that our null hypothesis that the difference is equal to 0, okay, that there is no difference. So we're going to take our observed difference, which is the difference of x bar, minus our parameter, which is going to be assumed that it's 0, so minus 0, divided by the standard error, which is going to be the standard deviation of the difference divided by the square root of our sample size, right? And that's going to be our how we calculate our test statistic. Okay, so I'm going to revisit this question about Mrs. Gallus. I'll just read it through quickly. You can advance if you already know this particular scenario. So Mrs. Gallus hoped to determine if the two versions of her AP Statistics final exam were equally difficult. Last year, she set up a randomized comparative experiment, and the data showed no statistically significant difference in the scores between the two versions. This year, she selected a random sample of 20 students from the large district and used a matched pairs design, where each student was given both versions of the test. For each student, the test order was randomized. Do the data provide convincing evidence at the 0.01 significance level, so that's alpha, that there is a difference in the average test scores between version A and version B of the final exam for the AP Stat students in this district? Okay, so we're only going to be able to draw conclusions for AP students in this district because that's where our population is coming from. So let's state what we are doing here. So we want to test. Our null hypothesis is that the difference is the mean difference is equal to 0, whereas the alternative would then be that it's not equal to 0. We're not sure which one's more difficult or easier, etc. And now I've got to explain what that mean difference is. So where the mean difference is equal to the true difference of version A minus version B in final exam scores for AP Stat students in this district using the third part and alpha equals 0.01. So just take a second here to remind you, if I enter my data into L, I entered mine in L3 and L4. And then L5, quick reminder, would be to subtract to find my differences. L3 minus L4. And it does the entire subtraction for me. I can run my one variable stat to get an idea of, is there a difference already? Just to kind of get a sense of what it is I'm looking at. So my one variable stat of L5 is showing me that right now the mean of the sample difference is 3.2 and that standard deviation is 3.533 right here. Okay, so what am I going to do for my plan? Well, if conditions are met, we will construct a paired t-test for the mean difference. I just need to remind you, make sure you are always using parameters for your hypothesis. If you ever use x bar or p hat, you are always wrong. You use parameters, which are your Greek letters mu. Okay, what else? So let's go through our conditions. First of all, random. A random sample of 20 AP Stat students was selected, 10%. I'm assuming that 20 is less than 10% of all students in the district. And because my sample size is small, I made a quantitative graph. I went with a dot plot, and I state the sample differences is less than 30, but the dot plot does not show any strong skewness or outliers. All right, so I'm going to do my do part now. So in the do, I know that I need my test statistic. So first I'm going to list what I just saw in the one variable stats. So the mean, sample mean difference was 3.2. The standard deviation of that sample, the difference was 3.533. All right, so my test statistics was, or is, my observed 3.2 minus my parameter, which I'm assuming that mu is equal to 0, that there is no difference, so minus 0 over the standard error, which is, from your formula sheet, is equal to the standard deviation of the difference, so 3.533, divided by the square root of the sample size, which is 20. Type that in, and let's see, I get 4.05. Okay, that's quite a few standard deviations away. It's kind of telling me that that's pretty unusual. So 0 here in the middle, 1, 2, 3, and 4 is like way out there. -1, -2, -3, -4. So really it's -4.05. Anything beyond that and beyond positive 4.05 is way over here. I'm going to label this as a t distribution with 19, let me fix that, with degrees of freedom equal to 19. Why? Because your degrees of freedom is one less than your sample size, so I need my p-value now. So my p-value, I can get several ways. It's going to be, I'm going to do it on technology. So 2 times, because it's two-tailed, 2 times TCDF. And let's pause for a second and go to the graphing calculator. So I'm going to go to stat, over to test. Actually, nope, I'm actually going to first show you this way. I'm going to run TCDF, which is in your distribution, so second vars. TCDF is option 6. My lower, -9999, my upper, actually, I guess it depends which side I'm looking at. If I look at my right side, I will do 4.05 to 9999, many standard deviations above, degrees of freedom 19. And I get a small number. So immediately I'm just going to multiply that by 2 because it's a two-tailed test. I need to double this. Okay, so it switches to scientific notation. You're going to need to write that as a regular decimal on the paper. So that my p-value is equal to 2 times TCDF, and I've labeled my calculator talk for the AP exam is equal to 0.0068. Okay, so that is a low p-value. So I will do my conclusion in just a second, but I also want to show you how you can run this entire test on your graphing calculator. So stat test, it is a t-test, just a one sample. So option 2, I'm going to go with data. My null hypothesis is that it's equal to 0. My data is in list 5. and I'm saying that it is not equal to, I'm going to go down and calculate. And here's everything I need as well. All right, so it tells me my test statistic, my t-value, my p-value, my sample mean, and my sample standard deviation, and the size of my sample. All right, so good stuff. Another way to check everything. Okay, so let's go on to my conclude. So what am I going to say? I'm going to say because my p-value of 0.0068 is less than my alpha, we reject the H sub O, we reject the null. Now put it in context. We have convincing evidence of a difference in mean test scores between version A and version B of the final exam for AP Stat students in this district. Okay, so that is an example of a paired t-test for means. Please reach out if you have any questions. It's important that you do some practice now.